Hey y'all, today we're going to be discussing concentration cells. Concentration cells are going to be galvanic cells that are not at standard conditions. So it's really important to understand how they function, and in the end, it comes back to kinetics and equilibrium to determine what the relative change will be to the voltage of this concentration cell. Today we're going to be looking at it qualitatively, and in the next video we'll look at it quantitatively. But let's start with a basic understanding of a battery as it stands. So like I said in the introduction, a concentration cell is a cell that is at non-standard conditions. And if you remember back to our original E cell calculations, everything assumed 1 molar concentrations of our ions and 1 atmospheric pressure if it happens to be a gas. When we are changing those concentrations, that is going to change the overall voltage of the cell. The point of this video is to give us an understanding of how. So let's start with a really simple example. Here we have 2 half cells that are both filled with a copper ion solution. The electrodes are both copper, and those 2 solutions are the exact same concentration, 1 molar each. Now, if we think about this as a redox reaction, copper ions would be oxidized and copper ions would be reduced. In this case, because copper ions have the exact same E of reduction and E of oxidation relative to each other, they would cancel out to have an E of cell of 0. So at standard conditions, this cell, this battery, would have a voltage of 0 because electrons aren't going to proceed in one direction or the other. But now let's change the concentration of the right side to 10 molar. Now in doing so, what we've done is we increase the concentration of copper ions. Thinking back to kinetics, that's going to increase the rate of reduction. The reason it increases the rate of reduction is because the copper ions are reactants in the reduction direction. So now on the right side, our reduction rate has gone up, but on the left side, it hasn't changed. This means reduction is happening faster in our higher concentration solution than it is happening in our lower concentration solution. This is going to create flow of electrons. Electrons are now going to be moving towards the side that's being reduced. That side with a higher concentration becomes the cathode. So we can think about this from a kinetics framework, or we can think about it from a Q versus K framework, or a Q versus 1 framework, as it were. We're going to talk about more that in the next video, where we're actually going to look quantitatively at Q and determine how it changes the voltage. But for now, let's stick with the kinetics thought process. So now let's change the copper in one of those half cells to zinc. So now our electrode's made of zinc and our ions in the solution are zinc. And if we have a cell made of a copper and zinc battery here, now what we need to do is think about the standard voltage and how that might change if we start changing concentrations away from 1 molar concentrations. So a standard cell with 1 molar concentrations for zinc and copper is going to be 1.10 volts. That's our voltage. But that assumes 1 molar concentrations of copper ions and zinc ions. What happens if we change one of them? Or what happens if we change both of them? Well, let's take a look. So in this case, what I'm doing is I'm increasing the concentration of the zinc ions to something greater than 1. It doesn't even matter how much greater than 1. Anything greater than 1 makes it at non-standard conditions. The copper, I'm going to keep at 1 for now. So when we look at the zinc ions, they are on the product side. Because they're on the product side, by increasing the rate of that process where they are the reactants is actually going to increase the reverse rate, okay? Now, what that is doing is it's essentially slowing the process in the forward direction relative to the reverse. So this is going to decrease the overall voltage of our cell, of our battery. So adding ion concentration to the product side is going to decrease the voltage below 1.10, but remember, it's always going to stay above 0 because of the fact that this is still going to be a spontaneous process in the forward direction. It's just a little bit less thermodynamically favorable. It's just not quite as energetically favorable in that forward direction because we are starting to now favor the reverse a little bit more than we had originally. So again, Resetting back to our original standard cell with 1 molar concentrations, our voltage would go right back to 1.10. But in this case, now what I'm going to do is I'm going to increase the concentration of my copper. Now the copper ions, if you look at my whole reaction here, my net ionic equation, are on the reactant side. By increasing the concentration of my reactant ion, this is going to favor, in terms of kinetics, the forward direction of the reaction. This is going to make the forward direction more thermodynamically favorable than it was before, which means that the overall voltage of my cell is going to be greater as a result of increasing the concentration of copper. So when we're making a battery, the first thing to understand is that we're going to start with standard conditions in most circumstances. However, in the real world, those concentrations are going to change. Think about it this way. As a chemical reaction happens, we are using reactants and we're creating products. Because we're using reactants and we're creating products, we're constantly decreasing the amount of reactants and increasing the amount of products. So what's going to happen to the voltage over time? Over time, the voltage is going to continually decrease down and down and down and down closer to zero. Where it's going to start and where it's going to finish is based off of what your original concentrations were and based off of the favorability of your reaction. But understand this, as a reaction runs based on what we've talked about today, you understand why a battery's voltage is going to decrease over time. Now let's take what we've learned and apply it in a couple of practice problems. Here I've got a new cell, all right, a new battery. This is a copper-silver cell. And in this case, we've got copper ions in one side and silver ions in the other, a copper electrode on one side, a silver electrode on the other. So in these two cells, let's say we start at 1 molar concentration. What would the cathode be? What would the anode be? Figure that out first. Then we're going to discuss what happens if we start changing concentrations. So did you have that the copper is going to be the anode where it's being oxidized and that the silver is going to be the cathode where it's being reduced? If you did, you're right. All right, remember these are based off of those E of reduction values. All right, copper's E of reduction is less positive than silver's, so it's going to be oxidized, whereas silver is going to be reduced. The voltage of this battery at standard conditions would be 0.46, positive 0.46. So now what happens when we start changing concentrations? Let's take a look at this. I've now doubled the concentration of the silver ions from 1 molar to 2 molar. It's a non-standard battery now. It's a concentration cell. So let's take a look at what that might do to the voltage. Where are silver ions? What do they do when you change them? Take a look. Make a prediction. Pause the video if you need to, and we'll talk about it. So did you predict that the voltage of the cell was going to be greater than it would have been at standard conditions? Well, if you did, you're right. And the reason, again, is because we've increased the reactant ion concentration. Silver ions are on the reactant side. It's the cathode, all right? They're being reduced. So increasing the concentration of silver ions is going to increase the rate of reduction, which is going to favor the forward direction more, and that's going to cause the overall voltage of this battery to increase compared to standard conditions. Now, here's another. Now we've decreased the concentration of the copper ions from 1 down to 0.5. What's going to happen as a result of this change in our conditions? Take a look, pause the video if you need to, and when you come back, we'll talk about it. Now, in this case, the voltage will also increase, but for a different reason. Instead of increasing the rate of reduction in the reactant direction, we're actually decreasing it, as it were, in the product direction. So when you think about it this way, what we've done is we've favored the forward reaction direction, but in a slightly different way. We've decreased the concentration of products. That's going to, relatively speaking, slow the reverse direction and keep the forward direction about the same. So the forward direction is more favored in this case as a result because of the fact that we've decreased the favorability of that reverse direction. So again, the reaction's voltage, or the battery's voltage, would increase compared to standard conditions in this case as well. So that wraps up today's video. Let's do a quick recap. Today we looked at concentration cells, which are batteries at non-standard conditions. We've already learned how to calculate the voltage of a battery at standard conditions. Today we did not learn how to calculate the battery's voltage at non-standard conditions, but we did learn how to predict whether it would be an increased or decreased voltage. In our next video, we're going to learn quantitatively how to predict what the actual voltage would be as a result of these changes. Spoiler alert, it comes back to equilibrium and a Q value is going to be calculated. Can't wait. I'd like to thank Grace Barnett for writing, filming, editing this video. I'd like to thank you guys for watching it. How's that? Was that good? I said one thing that sounded stupid, and I'll see you in the next one. If I only say one thing that sounds stupid, that's a win.